Hello, my name is Katya, and I am here to present the first portion of our presentation on the fundamental theorem of calculus, but I will be covering the historical development or the historical aspect of it. My partners are Marie and Lindsay.
Lesson objectives. By the end of this lesson, students will be able to understand the fundamental theorem of calculus, also known as the FTC, its proof, and how it connects to differentiation and integration. They will also be able to understand generalized Stokes' theorem, also known as GST, and its significance. Lastly, they will be able to recognize that the fundamental theorem of calculus is a special case of the generalized Stokes theorem and how the generalized Stokes theorem generalizes many fundamental theorems in calculus, including the fundamental theorem of calculus.
So, some key contributors of the FTC or fundamental theorem of calculus, we have James Gregory, Newton, Leibniz, and we also have Barlow. So, what is the fundamental theorem of calculus? Um, the FTC or the fundamental theorem of calculus, it connects differentiation and integration as inverse processes. It recognizes the relationship between calculating areas or integration and rate of change, or we could also say differentiation. It is based on earlier mathematical techniques and innovations. So pre-calculus era, before we had calculus, what did we use to measure things? For example, if we're looking for the area under a curve, what did they use? And basically differentiation before calculus, differentiation and integrations, they existed as separate ideas. They were not unified. Um, there were no unified framework to connect the two concepts. And ancient and medieval mathematicians laid the groundwork that we have today. Before calculus, we could say that in ancient Greece, um, Eudoxus and Archimedes, they used the method of exhaustion for areas and volumes. If they were looking for the area under a curve, they use, like we saw in class, the method of exhaustion. Um, it was a precursor to modern integration and limits, and it focused on practical geometry and physical applications. Um, Islamic and European scholars, their contribution were an extension of the Greek method, um, applied to geometry and astronomy, but there was still no framework or no formal um, framework for calculus. So before it was formalized, before differentiation was formalized, it was implicitly explored in velocity and motions problems. Um, Instantaneous rate were not formally defined, and tools for derivatives and limits were not present. We did not have those tools that we have today. Since solving mathematical problem had often required separate and labor-intensive methods, such as using geometric techniques like the method of exhaustion for calculating area or volumes, um, mathematician needed to find a way to connect differentiation with integration. And the the FTC, it bridge the gap between differentiation and integration, showing that they are inverse operation. Um, it provided a, I guess you could say, a framework to calculating areas, volumes, and rate of change efficiently, in a sense, transforming mathematical analysis. And in turn, what it did was set the stage for further advancement in science, engineering, physics by offering a more powerful computational tool. Um, so that way the work become less intense and it could be done a lot quicker. So looking at some of the key contributor of the theorem, we have James Gregory. He was the first to publish a geometric proof of the fundamental theorem of calculus in his Geometria Pars Universalis, and his focus was on the relationship between the area under a curve and the curve's antiderivative. And while his proof applied to specific classes of curves, it laid the crucial groundwork for later generalizations. Um, and our next mathematician is Isaac Bowell. He expanded Gregory's work by providing a more generalized geometric interpretation of the theorem. Um, he was the first to explicitly state the inverse relationship between differentiation and integration, and his work bridged Gregory's geometric method and the computational technique later introduced by Newton and Leibniz. Our next mathematician is Isaac Newton. From class, we know that he independently discovered the theorem. He introduced the concept of fluxorant or derivatives, influence, or integration. He demonstrated that differentiation and integrations are inverse operations, and developed calculus as a computational tool. However, as we learned, he did not publish his work. He delayed publishing his work, which limited his initial influence and which would also create a big problem with our next contributor. So our next and final contributor is Godfrey William Leibniz, better known as just Leibniz, and he independently discovered the theorem, but the difference between him and Newton was he published his. So our next and final contributor is Godfrey William Leibniz, better known as just Leibniz, and he independently discovered the theorem, but the difference between him and Newton was he published his finding. And in his findings, he emphasized clarity and generality. He introduced the modern notation um, for calculus, including the integral and the differential or dx symbols, making calculus more accessible and systematic. His publication would basically create a big problem with Newton, like we learned in class, um, which in a sense hindered British mathematics for over a whole century. So, to conclude part one of our presentation, the legacy of the fundamental theorem of calculus, we know that it revolutionized single variable calculus by linking definite integral to antiderivative, which this connection allowed mathematicians to compute area under a curve efficiently by evaluating the antiderivative at interval endpoints. And um, in essence, it introduced the idea that integral and derivatives are interconnected processes, forming the mathematical backbones for multivariable calculus. Thank you.
This is about Stokes' theorem. So Stokes' theorem starts by defining the integral for the line, and it sets it equal to the surface area, where S is the oriented smooth surface area bounded by a simple closed smooth boundary curve C with a positive orientation. By the orientation, if you notice, this is a three-dimensional slide. You have X, Y, and Z, and it has what we call a positive orientation. So it goes directly X, Z, Y. And we need this to be able to integrate the surface area. Okay, so in this example problem, I'm going to do x squared plus y squared plus z squared equals 9. And so you notice the first thing we do is we take the integrated value of f of x, y, and z, which is going to be equivalent to z times y cosine zi plus xe sine zi plus xe to the yk. So if you notice, the integral for the surface is the s curl f ds, and that's equal to the curl f dr, f times dr. And so if we take the function in this case and our original problem, we end up with the r of t being 3 cosine t. The next term would be s 3 times sine t, and the value of the z is 0. So we end up with that as a starting formula, which simplifies it a lot. If we begin, then the next, we take the derivative, which obviously gives us negative 3 sine t. The second term will be 3 cosine t, comma 0. So in this case, the integral of the f r of t is equal to 2 times 3 sine t cosine 0 e raised to the 3 cosine t times sine t, and 3 cosine t times e to the 3 raised to the 3 sine t. The result is 6 sine t, comma 0, comma 3 cosine t times e raised to the 3 sine t times t. This is evaluated from 0 all the way to 2 pi. So if we take the integrand 2 pi and from 0 to 2 pi, and we look at f as a curl t times r of t dt, we get negative 18 sine 2t dt. That is equivalent to 1/2, and that times 1 minus cosine. So negative 9 of the integral to t 0 to 2t negative cosine 2t dt. That results in the next line, which is negative 9 2 pi to 0 to 2 pi of t minus 1 half 2t, which is equivalent to negative 9 times 2 pi, which is equivalent to negative 18 pi.
Next, I will teach Generalized Stokes Theorem, GST. First is the introduction to Generalized Stokes Theorem, also known as GST. The Generalized Stokes Theorem generalizes the concept of the FTC to higher dimensions. In simpler terms, it connects integrals of differential forms over a manifold to integrals over its boundary. The theorem states that the integral of m dw equals the integral of epsilon mw. Here, m is a manifold, which is a generalization of a surface. W is a differential form, which is a generalization of functions, and dw is the exterior derivative of w, which is similar to the derivative of a function. I will allow students to visualize Stokes' theorem. In 2D, Stokes' theorem simplifies to Green's theorem, and in 3D, it simplifies to the divergence theorem or the curl theorem. Second, Stokes' theorem as a generalization of the fundamental theorem of calculus. In the 1D case, I will connect to the fundamental theorem of calculus. Stokes' theorem applies to integrals over manifolds, but for a 1D manifold, which is a curve, the boundary is just 2 points, and the integral of a one form over the boundary reduces to the difference between the values of the antiderivative at the endpoints. If we take w to equal f of x dx, then the integral of epsilon m w equals the integral from a to h of f of x dx, which equals f of b minus f of a, which is exactly the result of the fundamental theorem of calculus. In the last part of the lesson, I will connect the fundamental theorem of calculus to the generalized Stokes theorem. First, I will summarize the relationship. The generalized Stokes theorem connects integrals of forms over a manifold to integrals over its boundary. In the case of the fundamental theorem of calculus, the manifold is a 1D interval, and the boundary consists of 2 points, so Stokes' theorem reduces to the FTC. The FTC can be seen as a special case of Stokes' theorem when we consider the boundary of a 1D interval. Second is the application of both theorems. I will emphasize to the students that while the FTC applies to functions on a line, one-dimensional, Stokes' theorems can also apply to more complex scenarios and higher dimensions, such as curves in 2D and surfaces in 3D. I will then wrap up the class with homework. I will assign them to compute the integral of f of x equals 2x using the fundamental theorem of calculus. I will tell them to apply Green's theorem, which is a 2D case of Stokes' theorem, to find the area enclosed by a curve. I will then have them write a summary to summarize the relationship between the fundamental theorem of calculus and Stokes' theorem in a 1D context. At the end of this lesson, I hope that all of the students have learned generalized Stokes' theorem and the fundamental theorem of calculus, and how Riemann's sums prove the fundamental theorem of calculus.
Now, the main difference between Stokes' theorem and Green's theorem is that Stokes' theorem focuses on the three-dimensional value of a structure, and Stokes' theorem is the general version of Green's theorem. Stokes' theorem focuses on three-dimensional space, which includes integrals and curls. Green's theorem focuses on two-dimensional space. So let's look at the example below. If we look at the integral from b to a for df over of dx is equal to the f of b is equal to minus f of a. So this is looking at the integral of f times dr and the double integral of the curl f times ds. And this is going to be equivalent to negative 2z minus 2x minus 2y. So if we look at this from a mathematical point of view, y equals 1 minus x, and you can also look that y is equal to 0 minus 1 minus x. And x is equal to 0 as it approaches 1. And f of xy is equal to f of x of 1, 0, 1. And f of y is equal to 0, 1, negative 1. And the total area can be found by using the formula ax plus by plus cz equals 1. And that is equivalent to x plus y plus z equal 1. So z is equal to 1 minus x minus y. Let's equate that to the d. And y minus 1 minus x plus q dy is equal to the following. So we end up with a double integral of s of the curl f times ds. And that is equivalent to the double integral of d curl fr times the dA. So the curl of f times, the curl of f times the value is going to give us negative 2 times z times y, x times y, which is times 1 times 1 times 1. But that is equivalent to negative 2 times z plus x plus y. And that plus 1 plus 1 plus 1, which yields us to negative 2, parentheses 1 minus x minus y plus x plus y, which is equivalent to negative 2. So the integral of the surface area C times f times dr is equivalent to the double integral d, which is equivalent to negative 2 times of dA, which is equivalent to minus 2 times the area of d, which is going to give us 4 times 1/2, which is negative 1. So the integral of C of f times dr is equivalent to the double integral negative 2 times the d of a, which is equivalent to negative 2 plus 1/2 times 1/2, which is equivalent, like I said, to negative 1. The fundamental theorem of calculus is much easier. It is basically looking at the structure of two areas. So an example of this would be to find the integral between 8 and 1 of the following. So in this case, I have x to the 1/3 dx. That's the actual function. And so we take the antiderivative, which is 3/4 x raised to the 4/3 from 8 to 1, which is 3/4 of times 8 raised to the 4/3 minus 1 raised to the 4/3, which is equivalent to the 3/4 times 16 minus 1. And that comes to 45 over 4. So doing the integral for an area such as this and simply looking at the extremes, that is the value, 45 over 4. So this provides a much easier application of the dx of dy and the integration process as a whole. An overview of the key differences. So first of all, having finished with the fundamental theorem of calculus, you can see that it deals with a single variable and is very easily computed by taking the value of one extreme to another. In Green's theorem, it's slightly more complicated, is looking at a two-dimensional vector field. And Stokes' theorem is much more complicated with three-dimensional as a difference. So the primary difference is summarized, comes to the following. The fundamental theorem of calculus, which is the last one I just went over, it relates to a definite integral of a single variable function to its antiderivative. The area under a curve can be found by evaluating the antiderivative at the endpoints of the interval, such as in the problem we completed earlier, where we looked at x to the 1/3 and dx, and we looked at it from 8 to 1, or 1 to 8. If we look at Green's theorem, however, it disconnects the integral around a closed interval in the two-dimensional plane to a double integral over the region of the enclosure of that curve. In Stokes' theorem, we are looking now at the extension of the concept to 3 dimensions, relating a line integral around a closed curve on a surface to a surface integral of the curve of the vector field over that surface. So these are the primary differences between them, and the previous examples were computed to execute how they were solved.
So to demonstrate the fundamental theorem of calculus via GeoGebra, we would follow the following steps. Step 1, you need to define your functions. So for my demonstration, I'm using f of x equals to x squared, but it can be any polynomial. So you would input or type your function into the input bar and press enter. It will graph the function for you. Step 2, you create your integral. It allows you to visualize the area under the curve from point A to B by using the integral command. For example, you would type integral the function f, a and b, and press enter, replacing a and b with a specific value like 0 to 2 or 0 to 5. And as you drag it creates a slider. As you drag the slider, it shows you where the area is being shaded. So it basically demonstrates the area under the curve. Step 3 and 4, you need to show the antiderivative. And to do that, type f of x equals to integral bracket f of x, comma x, and close bracket, and press enter. This will graph the antiderivative f of x. Since we are going by the function that I use, it would be f of x equals to 1 over 3x cubed. And to evaluate the antiderivative at the bounds, basically you simply do f of b, which in the case of my example would be f of 2 minus f of 0. and you should be able to see the result displayed in your GeoGebra screen. And of course, the slider, it allows you to visualize the changes in the values from A to B. And this is what the graph looks like. And but if you want to play with it, you can just click on the link here and it will allow you to see it. These are our sources. We have about 7 different sources, but these sources are mostly focusing on the historical aspect of the fundamental theorem, which some of them we've covered in class already, so it shouldn't be too much